All right, in this first part of worksheet 10, we're going to be looking at applications of inverse trig functions. So in problem 1, we're told that a rocket is taking off vertically from its launch pad. An observer is 1,000 feet from that launch pad. So that tells us that the distance in this diagram that we've already drawn between the start of the rocket's launch and the observer, both of those pieces marked in purple, is 1,000 feet. So I'll label that distance to be 1,000. Next, he records that the initial angle of elevation of the rocket to be at 15 degrees. So he makes some measurement down here, marked in red. And that angle is 15 degrees. There's a 15-degree angle of elevation. A few minutes later, records the angle again. So after the rocket's been continuing to travel upward, and finds the angle of elevation to be 40 degrees. Meaning this larger angle should be 40. And the question that we're interested in solving, how much altitude did the rocket gain between these 2 points? So the piece then we are interested in finding should be this region marked in green. Let's call it H for the height. Now I want to look at the 2 right triangles that I have. One of these is the smaller right triangle with an angle of 15 degrees and an opposite side of y, while the other is a larger right triangle that has an angle of 40 degrees and an opposite side that I'm going to call x. So in order to actually solve for the height, which should have, or in order to solve for the height, I'm going to need to both know x and y. And given the way I've labeled these, h should be the difference between x and y. So I'm going to want to be able to set up an equation where I can solve for each one of those. And in both triangles that I was looking at, I know an angle, I know my adjacent side, which is 1,000 in both cases, and I'm trying to solve for the opposite sides. So I'm probably wanting to set up an equation that involves tangent. So I should be able to say that the tangent of 15 degrees is equal to opposite over adjacent. So that should be y over 1,000. And I can set up another equation, this time one that says the tangent of 40 degrees should be equal to x over 1,000. Meaning I can then get a value for both x and y. Y should be 1,000 times the tangent of 15 degrees. X should be equal to 1,000 times the tangent of 40 degrees. So if we apply that up top to get the value of h, it should just be the difference between those 2 pieces. So 1,000 times tangent 40 minus tangent 15. Tangent of 40 degrees minus the tangent of 15 degrees. And we can take that to a calculator and get an answer. I end up with 571.2 feet. All right, problem 2 reads, Alex walks from the train station heading due west for 2/3 of a mile to get to her job. Charlie leaves at the same time from the same train station and travels due south for 3 miles to reach her house. So we want to find the bearing from Alex's job to Charlie's house. So in the diagram labeled, that upper right corner is where I'm going to claim the train station is. The point A is due west of the train station, while point C is due south of the train station. A for Alex's job, C for Charlie's house. And we have to get the bearing from Alex's job down to Charlie's house, which means the angle that we're interested in is going to be this one, labeled in red. I'm just going to call it angle beta. So that angle is outside of the triangle that we have. To make things a little bit complicated, but not to worry. I can also label the other two sides. I know that Alex walked 2/3 of a mile, so that small side can be 2/3. I also know that Charlie walked 3 miles, so that larger side should be 3. And then I'll also come in and label an angle. I'm going to go with theta, because I'm going to put that one on the inside of the triangle. The reason I wanted to label theta is because that's the other angle I'm going to need in order to solve for my bearing angle, which is beta. So because those two angles are complementary to each other, if I put them together, I should get 90 degrees. I can have the equation 90 degrees is equal to theta plus beta, meaning that if I want to solve for my angle beta, I just need to get theta first. We should be golden. And theta is an angle that's relatively easy to solve for since it's inside of a right triangle. So looking at what I've got an unknown angle theta. I know my opposite side and I know my adjacent side. So I can set up the equation tangent of theta is equal to 3 divided by 2/3. Which means then that our angle theta ought to be the tangent inverse of 9/2. If we just simplify that ever so slightly. And we can come up with an angle there. Plugging that into a calculator and making sure that you're in degree mode, you should get 77.5 degrees. Bring that over to solve for beta. It should be equal to 90 degrees minus that 77.5 degrees, which simplifies to 12.5 degrees. So our final step is to put that into a bearing. So we know that our bearing angle is 12.5 degrees. And if I start from point A and go to point C, I'll need to be going southeast. So that bearing should be south 12.5 degrees east, or 12.5 degrees east of south. Problem 3. Brian is walking away from a street light and casts a shadow that is 9 feet long. Lamp is 10 feet off the ground and Brian is 6 feet tall. How far is the tip of the shadow from the base of the street light? So, go through and label some of the things that we were told at the beginning. We know that Brian is 6 feet tall. I'll put a 6 right there for Brian's height. He's that little stick figure. The lamp is 10 feet off the ground, so I'll put a 10-foot label over here on my lamp. And then also, I know that my shadow is 9 feet long. So this distance between Brian and the tip of the shadow is 9 feet. Meaning that the part that I'm interested in, which I'll label X. So X then is the distance between the tip of the shadow and the base of that street light. So this is a case of similar triangles, since I know these are both right triangles and they have the same angle over here in the corner, which I've labeled in red, although I don't need that angle, so I'm not going to give it its own label, because I can just set up a similar triangles equation. I should be able to say that x divided by 9 is equal to 10 divided by 6. Meaning then that x is 10 times 9 divided by 6, which should simplify to 5 times 3, which is 15. That should be in feet, since both of our other two distances were given in feet. All right, problem 4. An airplane is flying at 420 miles per hour and travels 45 minutes due west, then turns north and travels for 540 miles per hour for 1.5 hours. So I want to find the plane's bearing from its point of departure. So once again, I'm going to be looking for the bearing angle, which is always the angle that's measured from the north or south line. In this case, it'll be measured from the north line because the plane is traveling northward. And then I'm also going to need to label my two sides, since I wasn't given distances exactly this time, but instead I was told a couple of speeds and the times at which they're going. So I'll set up an equation. I want 420 multiplied by 3/4 of an hour. Right? 300. If I take my miles per hour and multiply by hours, I should get just miles. So if we do that, we ought to be able to get a number there. So that'll be 315 miles. I'll do the same thing for the other side. 540 multiplied by 1.5, and get yet another number. So 540 plus 270, that's 810. Just like the last bearing problem I looked at, I'm going to label that angle theta on the inside in green. And again, notice that the two angles I've picked in red and green are complements of each other. So 90 degrees should be the sum of theta and beta. So I'll set up another equation to get theta. I'm again working with my opposite and my adjacent side, which means I'm going to be looking at tangent again. So theta should be the arctangent of 810 divided by 315. And again, we'll take that to our calculator. Since we're working in degrees, we should probably be in degree mode. But when I plugged that in, and when I didn't mistake the 855 key, I got 68.7 degrees. So we'll use all that to solve for beta. Namely, beta ought to be 90 degrees minus 68.7, which simplifies to 21.3 degrees. So now I know my bearing angle is 21.3. So finally, I need to put that angle into an official bearing. And because this plane flew west and then north, I know that the plane's current location is northwest of its initial starting point. So my bearing should be north 21.3 degrees west, or 21.3 degrees west of north. Okay, problem 5. Due to a fog, a boat is going to leave the dock at a bearing of 43 degrees east of north. It'll sail for 12 miles. Then the boat turns 90 degrees, sailing 80 miles southward. What is the boat's bearing from the dock? So, bit to unpack here. Suppose we'll start from the beginning, where I know that this angle should be 43 degrees, since that's my bearing. 43 degrees east of north, shown here in orange. Next, I want to talk about the right angle that shows up in that triangle. I'm told that the boat turns 90 degrees and it's southward. Right, so notice that it does not say that the boat turns to be due south. It says that the boat turns southward, right? So after that boat moves in its original northeast direction, if it's going to make a 90-degree turn, it could go one of two ways. And I could describe those two different ways as northward or southward. suppose I also could describe them as eastward or westward, but I opted for northward versus southward. So when we say that the boat is going to turn 90 degrees to the southward, that means of the two 90-degree turns it could make, I want the one that goes in the southern direction, which again is not due south, just 90 degrees southward from its original northeast bearing. So the other pieces that aren't on here yet are the distances. I know that this longer part of the trip was 80 miles. The shorter part of the trip up here is 12 miles. And we'll label a couple other unknown angles. I'll use green for theta again, being that interior angle of the triangle. And red once more to label beta, which will be my unknown bearing angle. So in the previous problem, I had that theta and beta, the two angles labeled in red and green, were complements of each other. This time I have that all three angles, that 43 degrees, the green angle, and the red angle, are supplements of each other, since I can get a complete angle going from due north to due south by adding up those three angles. So this time I have the equation 180 is equal to 43 plus theta plus beta. Which means I'm still just going to be looking for that angle theta again. And once I have that, I can go plug it into this equation and get my bearing angle. So apparently due to some amount of lack of creativity, I end up with yet another tangent problem, since I know my opposite and my adjacent sides. So theta should be the inverse tangent of 80 divided by 12. And so we'll pop that into a calculator again. And when I did that, I got 81.5 degrees. So I'll bring that over to my angle equation. 180 degrees minus 43 degrees minus 81.5 degrees. And that should get us 55.5 degrees. So now I have to put that angle into a bearing, and this boat ended up southeast of its dock. So the directions will be southeast. So south, 55.5 degrees east. Or 55.5 degrees east of south. Then problem 6, got a family traveling on the highway in their RV at a bearing of 46.2 degrees west of south. They're going to travel on that road for an hour at 70 miles an hour, then turn 90 degrees northward, travel on that road for 2 hours at 50 miles an hour, and then we'll ask to find that new bearing from its starting point. So the first piece that we'll label will be that 46.2 degrees, where that was a bearing. So I should measure it from the southern line, so the due south line. And we're traveling along that road where we make a 90-degree turn northward. which again does not mean due north, just when I have to make a 90-degree turn, and I have to distinguish between the two directions I could go, I want the direction that is northward from that spot. So we'll turn 90 degrees northward. Next, if I talk about those distances, if I travel for 1 hour at 70 miles an hour, I will travel 70 miles. Then if I travel for 2 hours at 50 miles an hour, I'll travel 100 miles. Put those two distances down. Then also label the interior angle, theta, and the bearing angle I'm interested in solving for is in red. And again, that bearing angle should connect my direction to the due north line. So if I set up an equation that I'll use to solve for beta, I know that it should be 46.2 degrees plus theta plus beta, and all of that is equal to 180 degrees. So I'll need to first get that interior angle. Looks like, again, it came out to be a tangent problem. So theta is equal to the inverse tangent of 100 divided by 70. Or you could simplify that to 10 over 7 if you felt so inclined. Either way, in a calculator, making sure that we're in degree mode, I got 55.0 degrees. So we'll drop that new piece of information into our equation for beta. So that'll be 180 degrees minus the first bearing angle, which is 46.2, minus the interior angle of that triangle, which is 55.0 degrees, and end up with a number and I got 78.8. So again, that's our bearing angle. So now we'll just need to put that into a bearing. So from my initial starting point, which is where that compass heading is drawn, my RV ends up to the northwest of its initial position. So the direction in my bearing should be northwest, with the bearing angle of 78.8 degrees put in the middle of it, or 78.8 degrees west of north. Right. In problem 7 and 8, we'll look at similar triangles. So if we have similar triangles, let's look at how things should be labeled. First, in similar triangles, or anytime we have a specific triangle naming convention, we often use capital letters like A, B, and C, as in that first triangle on the left, to represent angles. And then the corresponding lowercase letters can be used to denote the sides opposite each of those angles. So side A should be opposite angle A. In this case, it looks like side A is 14. If we jump over to the right triangle and label its corresponding side, side D should be opposite angle D. We can do the same thing for sides B and also E, and side C is opposite angle C, side F is opposite angle F. So I've also color-coded these in such a way so that the similar sides in each triangle ended up with the same color. Since we're told that triangle ABC is similar to DEF, we can use the order that those letters are in to establish the similarity that occurs. So A and D are similar, B and E are similar, C and F are similar. And what we have in similar triangles, so I suppose we should define what that means, is that all of the angles in two similar triangles are the same. So angle A has the exact same measure as angle D. B has the same measure as angle E, and angle C has the same measure as angle F. The thing that we don't necessarily know about similar triangles are just exactly how big each triangle is. All we know is what its shape looks like. So we're just missing scale. But what we do know is that the ratio between similar sides must always be the same. So I could set up A over D and say that that must be the same as the ratio of B to E, or B over E, which also has to be the same as the ratio of C to F. So I end up with this three-part equation. And while each of those are true, it's impractical to use all three pieces in a single problem. So anytime we're actually going to be applying this rule about ratios in similar triangles, I'll just be picking out two of the three pieces that I need. So I'll choose one ratio that I know everything about, and also a ratio that contains the side that I'm interested in. So since I know sides A and D, so I know the two blue sides, and I'm looking for the green sides, I'll use the blue and the green parts out of that similar triangle setup. So C divided by 15 must be equal to 14 divided by 21. And hang on, let's make sure we label these right. And we got it right. 14 divided by 21. Yep, this should be A divided by D. So solve that thing for C. Suppose I can start by simplifying that 14 over 21 and say that that is 2/3. Then I'll multiply it by 15. By doing so, 15 over 3 is 5. 2 times 5 is 10. So that's my missing side C. So if we look at problem 8, this time we're told that triangles DAR and KMR are similar, and I want to find the length of Y. I just want to be a little careful with how I set this up. Since the actual side lengths I'm going to be interested in for the large triangle DAR are going to be the ones that I'll label in green. So from D all the way to R actually has a value of Y plus 11 as opposed to just 11. Also, that distance from A to R has a value of 30 rather than 16. So I'm going to be a little careful with how I set that up. So if I go about setting up ratios as established in the previous problem, I could end up with y plus 11 divided by y in this case will be in purple. And that should be equal to 30 divided by 14. So this time, rather than using the colors to note specific similar sides, we're using purple to talk about the smaller triangle, while green is talking about the larger triangle. But then we'll need to solve this thing for y, which means multiplying some pieces around. I'll have 14 times y plus 11. And on the other side of the equation, that's equal to 30y. And then we'll start looking to solve this thing out. So 14y plus 156 is equal to 30y. It's 14 times 11, should come out to 156. Combine some like terms. 156 is equal to 16y. And then I'll make that division and say that y is 156 divided by 16, which comes out to 9.75.